that some people love it and some people hate it. Right? That's not the definition of love hate, but you get the idea. Logic proofs is something that maybe you did in a geometry class. You'll if you do computer science, you definitely do stuff a lot of stuff with logic, but in probability, we don't do nearly enough logic, nearly as much logic as we should, right? Because probability is all completely based off of propositional logic, right? So the ands, the ors, the if-thens, if and only ifs, all that good stuff. All right, to get started with this, we touch on Venn diagrams, and you may be familiar with the union notation and the intersection notation. Mostly the union, because you've seen that with domains, domain and range. In interval notation, you have the union, but the intersection, you didn't really do too much with outside of an Algebra 1 class. All right, it comes up more frequently in math than the courses that we teach here would make it seem. All right, so I figured I would take some time and walk you through how to create Venn diagrams for certain situations, because it will come up again when we discuss different forms of probability. All right, so the intersection is the and. So it's the equivalent of an and. All right, and if you think about an intersection in everyday life, I mean, you got one road going this way, one road going that way. The intersection is where they cross. I mean, if you think about it in a math class, you've touched on that plenty of times. Two lines, where do they cross on a graph? All right. What we're talking about here is a commonality between two sets. All right, so commonality between two sets. Now, pardon, if I let my first circle here be A, and my second circle here, I let that be B, then the intersection is going to be where the two overlap. All right. The U stands for, it's overused because we're using U for something else, but this is the universe. All right. Also known as a sample space. I over-M'd my M. Sample space. So in some Venn diagrams, you'll see U at the bottom, in that bottom right-hand corner. Some of them you'll see S. All right, they're interchangeable. All right, this is the set of all possible outcomes. All right, just because we're only concerned with sets A and B doesn't mean there isn't a set C, D, E, F, infinite. Right? Well, actually finite, but finite large. Right? Probability is a finite branch of mathematics. Right? So there's really no practical infinity. Right? So we just use some finite large value. Theoretically, of course, infinity is a possibility, but in the case of countable discrete mathematics, infinity is not really considered. All right. So what I'm going to do here, and this is probably not something you can do. Don't trace over the box. I'm just doing this to make a copy of it. I'm going to just use shading to show you how those intersections work, intersections and unions. So this is the drawing part of the unit. All right, so I'll just do it off on the side here and make a copy of it so I have it. Like I said, not something you could do, but for demonstration purposes, I'm going to do it. All right, so I have two Venn diagrams. When they say the intersection of two sets denotes the elements that the sets have in common or the overlap, what they're saying is if I take set A and set B, and merge them together, that overlap, yellow and blue make green, that overlap would be the intersection of A and B. All right, so this is A, A intersect B. Let me go with a thinner marker there. All right, so that's just this little bit here, which I guess I could shade in green. Get a little light green here. You don't need it now, but I have a whole class set of colored pencils that we're going to make use of in the coming days. Right. Now, I could actually work off of the same diagram here, this one, for the second example. Well, not example, but the second concept. But I'm going to just kind of do it from scratch anyway. So I have two sets, A and B, two Venn diagrams, each with its own designated set. All right, so again, A is, I'm calling A the yellow, B the blue, and again, if I merge the two sets, I'm going to get the same diagram. But what's happening here, when you talk about the union of two sets, you can see it merges them into one larger set. I mean, that's in the notes. But really what that means is that A is bringing its assets to the party. So is B. And then we're combining the two sets to make one mega set. All right. The union is the case of an OR. All right. So I'm just leave that separate for now. So this is the case of OR. So all parts of each set. I'll just do that and do that in red. All right, so all parts of each set is what we're looking at when we find a union. All right, so the word or in everyday life can be kind of annoying in comparison to how it's used in math, or maybe the math is the annoying one, right? If I tell you that it's either this or that, and the presence of the word either makes it a choice. But if I tell you it's this or that, it could be this, it could be that, or it could be this and that at the same time. So if I told you that I'm wearing a hat and a hat or sunglasses, it makes you think that if I'm wearing a hat and sunglasses, that wouldn't apply because it'd be a choice, right? I'm either wearing a hat or sunglasses, now it is a choice. But if I say I am wearing a hat or sunglasses, if I walk in a room wearing a hat only, sunglasses only, or a hat and sunglasses, then I have satisfied the rule of or, all right? So what's happening here is we take, yeah?
If you're wearing a hat and sunglasses, how is that one or the other?
Well, that's the thing. The either or would be one or the other. But if I don't use the word either, then it changes the definition, the math definition of it. It allows for the overlap. Right? So if there is a commonality between the two sets, that would also be included. All right. So what we're doing here is we're looking at, again, sets A and B. Any part, when I merge the two sets, any part that has shading whatsoever, so I merge the two sets, any part that has shading whatsoever would be considered part of the union. All right. I've always used marriage as an example. I mean, it doesn't always land on the high school level, but you can kind of conceptualize it. You know, you have two people get married, right? Person A has their own stuff, person B has their own stuff. And then when they get married, they buy stuff together. All right? So if I say, what belongs to the couple, the married couple? Well, everything they brought in individually and everything they bought together. Right? So that allows for that overlap to be included in the set. Right? That, unfortunately, or for better or for worse, I don't know, that's the best example I got. Jack, question?
So the whole thing you label A, union B?
Yep.
The whole thing?
Yeah, the whole thing, everything I shaded there is A union B. Yeah, right.
Would it just be A plus B?
A plus B.
It's the middle.
Minus the middle? Sure. Yeah.
One is one.
If you're looking for probabilities, we'll get into that, yeah. But in terms of what's actually included in the set, yeah. If I were to looking for the probability that, you know, the outcome is part of set A or B, then we don't want to double count the overlap, so yeah. Now, the last one here, I probably should have led with this, now that I think about it. It's probably much easier. So, A, if I'm letting A be whatever's in that circle. Now, this is something to keep in mind, very important. When I label this A, I put the A here just to not overlap with part of the circle. But technically, this A, when I say A, I'm talking about everything in this circle is A. All right, the issue is some of what's in this circle here is part of B. But when I say A, I'm talking about everything in this circle, including the overlap. But I put it here just for kind of cleanliness, I guess. All right. Within the universe, everything that's not A would be anything that's outside of the circle A. All right, I'll use a different color here. So that would be all of this. Which admittedly takes a few seconds to draw. Shade. All right, so that would be not A. All right, but just as a quick aside, I'm just going to create an example that takes you through the structure of the Venn diagram in its entirety. Because you may be concerned with, okay, so if all of this is A here, all right, I'll use my thing. If all of this is A, then what's this little half moon part? Well, it's A that's not B. So we would say that this part here is A and not B at the same time. Right? It's the intersection of A and not B. We already know that the overlap is A intersect B. Then the other half moon, well, if we know the whole thing inside this circle, everything inside this circle here is B. If I just wanted this half moon here, I'm talking about B and also what? Not A. So B intersect not A. All right. And again, this whole thing is the universe, so I'll put the U there. We also have everything that's not in the circles that could be identified. We can name that too. All right. So just going back to the union, everything inside of this circle here, all of this stuff here, it's kind of hard to identify by labeling, but I'll just write it off on the side here. This is A union B. So if I want everything outside of those shaded circles, what do I really want?
Not A, not B.
Not A union not A union B. All right. This is like academic language. We would say that it's not the case that it is A union B. All right. So if I say not A union B, you could conceivably interpret that as not A union B. All right, but that's not what we're really saying here. We're saying we know where A union B is. We want not that. We want everything else. All right. So we would say it is not the case that we have A union B. All right. These two things are not the same. All right. Now, what is equivalent, and I'll show you this. I get to it on the next page, but I'll just steal my own thunder right now. So this is the same as distributive laws still apply when it comes to set mathematics or arithmetic, set notation. I can distribute that negative through the expression, through the union. All right. So I could say not A intersect not B. Those mean the same thing. All right. So not A union B is the same as not A intersected with not B. All right. That's known as De Morgan's laws, or one of them. Well, one of De Morgan's laws. All right. So on the next page, we have some more diagrams, and you can see I kind of, as you go forward through it, I steal my own thunder a little bit. You see we have this, we have this. We'll come back to that in a minute, but before we get there, we'll tackle it. Numbers 1 and 2. On a Venn diagram, shade the regions corresponding to A union not B. And so what I like to do, and I know that this is probably annoying on your part, not on your part, from your perspective, and make sure I'm directing the annoyance to the right location. It should be up here, not out there. All right. So because I can do this on my device, it's like, oh, it's so much easier for you to do it. You can visualize it. We have to do it with pencil paper. That's why we're going to get the colored pencils involved before too long. All right. So what I like to do is first keep in mind, so it's really just kind of a thought process. Keep in mind that when it's an intersection, you're looking for overlap. Most people are fine with that one. When it's a union, you're looking for any part that's shaded whatsoever to be part of your final set. All right. So I'll use a little color key here. So here's my A, my set A. All right. Then I have set not B. So everything except for B. All right. Set A, set not B. Regardless of whether it's a union or intersection, you're putting it all together. The union is saying any shading whatsoever when graphs are graphs are merged. All right. So any part that contains any shading whatsoever is going to be part of your combined Venn diagram. Regardless of whether it's yellow, blue, or green, it's all going to be part of the set. All right. Now, some people are better at visualizing that without drawing the pictures than others. I kind of go back and forth. In some instances, I'm like, oh, I see it in my mind. This is great. And then in other circumstances, I'm like, I can't see this. I'm really aggravated. Let me get the colored pencils out. All right. So regardless of how you want to shade it, now you can do like the cross hatching or whatever. But everything except for that little half moon of B. Oops. I said everything except for the half moon of B, and then I proceeded to not shade in the half. The relevant parts. So you can do it like this too, but I find that it's easier if you kind of visualize it, or at least come up with a diagram first.
Why is the middle part shaded if it's A and not B? Because the middle part includes B.
The middle part includes B, but it's only there because it's part of A. Since it's the union of A and B, any asset that belongs to A is going to be part of the solution, including the part that's excluded by B. And that right there is probably the trickiest part of this concept, right? Being able to just kind of get a hold of that in your mind, all right? Now, the good thing is, for these questions anyway, I'm not going to say for the topic at large, but for this set of questions, the diagram that I drew, the merged diagram that I drew for number 1 also applies to number 2. We're just doing something completely different with it. Well, completely, maybe not, just different. All right. So here we're looking for just the overlap. All right. Just the overlap. So that's that little half moon inside of A. All right, yellow and blue make green. I'm just shading where it was green. All right, so it's still this diagram because it still has the same base ingredients, A, not B. I'm just doing something different with it. All right. So I guess I could just kind of put this down below. All right, a little scratch work goes a long way with this. We've already talked about number 3. All right, the union of A and B is everything contained within A and B, individually and collectively. Not A union B would be everything outside. Now on the previous page, I told you that it is not the case that it's the union of A and B. That's the same as saying not A intersect not B. So we'll look at that now. So ultimately, whatever I get as a Venn diagram for this one should match this one. All right, we do it right. All right. Otherwise, De Morgan's law does not apply. And since De Morgan's law does apply, it must be the case that these two Venn diagrams will be the same. All right. So, got my pictures. I'm going to shade not A. Again, color coding. So not A is everything outside of A, regardless of whether it's in B. Not B is everything outside of circle B, regardless of whether it's in A. All right. And again, whether it's a union or intersection, doesn't matter. We're still merging the two Venn diagrams. All right, so when you merge the two Venn diagrams, again, just take note of what it is you're looking for. The intersection means that we're looking for the overlap, right? Right, so just the overlap. All right. So yellow and blue make green. Everything outside of the two circles, but still within the universe. All right. And to answer the question that nobody's asking, and I don't know that I would, it's always going to be contained within the universe. Right? There's never going to be a circumstance where I'm going to say outside of the universe. So you won't see a not you. Right? That would be literally infinite. Right? Because then I would have to shade literally every part of this paper except for what's in this box. All right? So that's, I mean, it's fun to think about, but it's not something that would be applicable to really anything. Yeah.
So the key to doing it is basically just kind of splitting up each component and doing it one at a time.
That's the way I like to do it. Yeah.
So you get a visualized theory.
Yeah, that's my feeling. I have worked with many people over the years that will just look at the scenario and be like, well, it's there. Like their brain is just wired in a different way, and that's good. Yeah, that's great. Great for them. I'm probably 50-50 on whether or not I can do that. Right? Most of the time, especially with, these are, no offense, they call these the basic examples. It's basic in the sense that when we get to more complicated situations, you'll look back at these and say, well, I know what A union B looks like because we've done it 1,000 times. All right. So like basic arithmetic, when you're first learning it, it wasn't the easiest thing in the world. But then after that, it was like, oh, okay, like I'm fine with it. It's like, that's so second grade. Right. This will feel like that later on, but we got to get through the formative stuff first. Thank you. All right. So